Okay, hey Sam, welcome back. And yeah, I was just googling out here and there, just trying to pass my time, and I came across Aho-Corasick algorithm, which is mainly used for searching if a given letter is present in the not a given letter, if a given word is present in the given sentence. And yeah, I found it to be a very cool algorithm, and it uses a very rarely used data structure called trie. Trie is nothing but a prefix tree. In it means that you will have a node, and node will not actually contain numbers, but it will actually contain letters itself. And yeah, prefix trees are actually more to tell. They're not like having only two children; they can have n amount of children. So I thought let's just implement it and go over it once because yeah, it was fun. So yeah, Aho-Corasick. Yeah, the name itself is very sick. I know that, and believe me, the algorithm is also like very cool and sick. So yeah, so what you like, you will have a try node. But let me go over what a try node is. Imagine. And I'm not a coder, so I could not like manually code up a pre-visualizer. So I'm just hijacking this one, and this is a very good way to visualize. But whenever you're doing something, make sure that you can visualize it and then go forward. So imagine you have a cat. So when you put cat inside a prefix, it will be like this. So you have a dog. When you put dog inside a prefix, you will see that a separate node is created. But when you try to put doggo, so what will happen is since dog is already present in the prefix tree, it won't create a new node for dog, but doggo for it will just hijack the old dog one, and after G, it will tell okay, there is another node called G, and another node for do. And if you see the tree node, then you'll see that each letter is actually its own trie node. So now let's try to do that. So each trie will have a trie node. So yeah, first let me code up a trie, and I hope you understood what a trie is. And using tries, Aho-Corasick uses I mean, Aho-Corasick uses tries to find out if a given letter is present in the world. And since I made a video on rolling hash, it makes sense that I made a video on Aho-Corasick. So yeah, class trinode. Trinode will have only two things. And again over here, if you saw, it has only two things, which is child and the end of the word. The green blocks are end of the word, and others are child. So the root has two children, C, and let me insert one more good one. It means DOGI. So you see that after DOG, it creates a new branch and inserts I over there. So yeah, each node will have a child and it will have another property called end of the word, denoting that if it is actually the end of the word. And if I put one more, you see that DOGI is also present. So I is marked as end of the word and DOGII is also present. So the last I is also marked as end of the word. So yeah, so again, now let's define the time. And then that's, yeah, again, having online helpers like Tableau or something is really useful when you're coding. And in this current age of AI, if you don't use those tools, then you will be left behind. So yeah, so each node will have a children. It will have a child or children, and you can use arrays also for this. But it not only increases the time complexity, but also makes the code more not difficult, but more lengthy to write. So let's just utilize a dictionary. And dictionary will store each operation, like each element very efficiently and make operations also very fastly. So yeah, you'll have a children, and each node will also have another property code. Is word end. I hope I could type today. It will initially be false. And now let's define a try itself. So yeah, now just think about it. A try will always have a root. So initially, what will try? Yes, initially I will have only one thing, which is a root. So what is root? Root is actually a trinode. So it's our perfect dot trinode. Yes. And now yeah, let's go insertion operation. I hope you understood how insertion works. So it will just it will be like it will be in G and it will try to insert O. And if O is not present, it will create a new trinode. And after inserting the trinode, the pointer will go to O. Again, it will go to G. After insert O, if you try to insert G, and after you try to insert G, if you try to insert one more G, it will go left. But after inserting G, if you try to insert an I, so it will see that yeah, after G, there is no another node called I. So let's create a new node and go over there. So that's how a try node works. So that's the insertion node. So not set, it's there. Insert. So what you insert? You insert a word. And since I'm using insert inside a class, so I have to put style. This it is just like the this keyword in Java. So what you have to do? Yeah. So what you have to do? So declare the node. Node is actually the root. Initially, the node will be the root, and for each letter in the word, don't use the I, but don't even though you're using things like admin enroll, don't directly and blindly type tag on whatever session you give because it's not in the form of terminator or something, and it won't always be proper recommendation. So yes, yeah, again, if the current letter, if the current letter is not, if it is not in the node dot children, and so I hope you understood why it was, if not letter. Since Python gives us more robust language, so if the current letter is not in node dot children, so what you have to do? Create a new try node at that position. So node dot children. If you are using arrays, then you have to do dot append. But since I'm not using arrays, at the position letter is a new try node. And yeah, again use the keyword of Java. So particular try node, yes. And after inserting the try node, go to that point. So children at the position database. And after inserting the entire word, just set that point to be at the end of the word. So you have another property on try node called is word end. So yeah, just set it. Uh, take the current node. So is word end and set it to true. Telling that yes, you have actually reached the end of the word. And now next let's do for search. Let's do for search and search will again have self and the actual word. And yes, so what you have to do again for searching, we actually know that you're in the root node and you want to go to D first. And after going to D, you have to go to O, and then after going to O, you have to search for G. And yes, so you are actually searching for the word. And how to search for the word is you will actually have the field node. And if, imagine you are searching for dog. So you first you check if D is present in the children. And if D is present, then you will tell that yes, go to the search for the next word which is O. And in other words, check for the children of D. And in the children of D, O is present. Then go to that node or go to that node. And after you reach O, you have to search for again G. And yeah, again we'll see that G is actually not only present in the children, but it's also marked as uh, word end. So if you see over here, after reaching the end of each word, you will mark that current word as that current node as is word end to true. So again, I hope you understood. And if the word is not present, so what will happen is, and imagine you're searching for what will tell CAT cats. You're searching for cats, so you first pick A, C, and then from C you check for children of C which contains A, and you'll see that A exists. So you'll check for children of A which contains T, and T is actually the end of the word. But again, you'll continue because I is also end of the word, and I also has children. So yeah, again after reaching T, you'll continue and you'll search for yes, and you see that yes is not actually present in the children of T. So you'll actually break out of the loop and tell that yeah, the current word is not present. So I hope you understood how it works. So first, yeah, do the same thing again. Initialize the root. Root is actually the initialize the node. Yeah. Yeah, you can initialize it as root also, but after each iteration, it will technically not be the root, but you'll be calling it root, and it's not good practice. So root. And now go through each letter in the word. In the word. So what you do is, if the letter is not present in node or children, so it's not present in node dot children. That means that that is actually not a letter present at all. So in this case, don't directly copy the above part and add a new try loop. You just return false. Or else what you do? Tell the node to go to that child to node dot children. Is the position. Yes, now we are telling the node to point to the child node. And after that, even after reaching the end of the node, yeah, let's again go over this. DO. Again, let's go over DOGII example. Imagine you are given the letter DOGII. So you first check for D, after D you go for O, G, I, and then reach I. But actually I is not end of the word. That means that DOGII is not actually present in your given set of sentences. So what you do is you will have to return false in that case. So how will you get to know that? You obviously have declared the is word and property over here. And since is word and is actually initially set to false, it will return false. But if it was DOGIII triple I, then what would happen is after reaching the last I, it would tell that yes, the last I is actually set to true, and that means it is actually the word. So you have to return true. So what you can directly do is return no dot is word. Yes, this is actually how this is actually the code of the entire try. And on seeing the hearing the name try for the first time, it might seem like very difficult data structure to learn, but it is actually very easy. And again, the entire code is about how much you tell 9 minus 26 minus 8, which is about 18 lines. And again, there are a few spaces over here. Again, minus 2 over that. And then now the entire try is defined, try node is defined. And now actually let's go to the crux of the stuff which we were about to do, and which is actually using Aho-Corasick algorithm to search if the given letter is present in the sentence, not if the given letter, I mean the given word. Yeah, even you can choose it to be a letter. It makes no difference. So yeah, let's call us find words because we were actually trying to find words in the sentence. Again, keep everything verbose so that you'll understand what is happening the next time you go to check for it. And over here, there is no need to write it as self because it is not actually defined inside any class. It is standing outside the class. So you'll have two things over here, which is words. Let us actually take an array of words rather than a single word to check, and then you will have a sentence. So again, what you have to do again first initialize the try. Try is actually our dot try. It's not initially it is not the try. Again, don't directly do auto recommendation. The initial word is actually try. And now what you have to do, go through each word in the given array of words and create a try node out of it, like create a new try out of it in the same way which has been done over here. But you will add CAT. So you have to do that part, right? So first we will finish that. So for word in words, you have defined the insert method over here, and since insert actually takes the word itself and it breaks down the letter, there's no need for us to like go through each word, each letter of the word and then insert it. You can directly insert the word over here. So yes, believe it or not, you have actually completely coded this part up now, and this part is actually ready. That means we directly remove everything, and we'll keep it empty for some further example. And now, yeah, so now what you have to do? You have to go through the sentence, and for each index of sentence, you have to check if the word exists. So for I in range length of sentences, you can't directly do for I in sentences because you actually need the index to print out the words which are present. So let's store it in array called indexes. Yeah, for I in range length of sentences, what you have to do? First, take the try node and try out. Yeah, take the root of the try which you have already created and set it to a node. Yes. Now you are actually pointing to the root of the try. And so now what you have to do for j range I to length of sentences. Yeah, again, now just think what will happen. SEMP sentence. You're using only one sentence. Yeah. So now just think what is supposed to happen actually. So first, what you have to do is check if the try node. So just let us make it more verbose. Letter is sentence at the position j. And yes, now what you have to do is just think about it. So first you have to check if the letter is actually present in the node itself. So you might have a try node like you have a try node of called cat. Yeah, we have two try nodes like this, and Yes, now imagine your even dog. It is pretty obvious that dog is not actually present in the root itself or anywhere. Since dog is not present in the root, you can directly return false. And this holds true for everything. So even if you had CAT, what will tell a CATING. So imagine you had a word called CATING, and you will see that after C is present, A is present, P is present, but I is not present in the children of P. At that instant also you have to return false because yeah, you can't form the word. So letter is sentence of position there, and if the letter is not present in, it's not present, so it's not present in the node dot children. So that means that you could not find the root, or you could not that not the root, you could not find the actual word. So yeah, don't do this because this is actually syntactical error, mainly because uh, mainly because it's actually not being called inside a function. Like you don't want to write return false over here. You have to break out of the for loop. And if the letter is actually present in the children, then point the current node. So take the current node and point it to node dot children at the position letter. Yes. Yeah, it's actually that much only. And after doing everything, you have to just check if the node which are currently present on, if it is the word end. Node dot is word end, right? Is word end. So at this instance, what you have to do is just you have actually found the entire word itself. So break out of the loop, but before breaking out, you just store the indexes, and we have conveniently declared the indexes. Just append the value of I and j. And since many programming languages have non-inclusive right index, so you have to j plus one. Or while printing, you have to do print start to end plus one, and that does not look that good. So directly let's take care of that also here. And believe it or not, this is the entire algorithm. So now just let's go through each indexes for start and print in. So now let's print sentences from start to end. And yes, this is believe it or not, this is the entire algorithm, which is totally about 50 lines in including the white spaces. Also, if you remove that, it will become much more smaller. Now let's just check it out. So find words in sentences, and yeah, first have an array of words, and then the sentence. So let's have you have a car, and a bike, and helicopter, and let imagine that you have to check if car, bike, helicopter, boat, and human actually exist in the sentence. So and yes, this is a very good sentence. And yeah, now let's just run the code once. Run the code. Yes, and you see that car, helicopter, car, human, helicopter. And why is that? So bike is actually not present in the sentence. So it's telling that the bike is not actually added over here. So rather than this, you can also put it in a set, or you can just return the indexes. It depends on what you want to do or what your edge work, what actually you want to do. Some questions, some place you might want to implement just returning the index, or some place you want to return the actual word itself, and some places you might not want duplicates like over here. I'll explain why there are two cars and two helicopters, but only one human and no boat. And so yeah, but let's go through the sentence. Let's add this. Let's do one thing. Let's add the entire. array list. Um, let's do a try out of the entire. This is actually a good example, but since we don't have branches, it will directly be four array tree now. Let's do one more thing. Let's actually add one more. Let's add Helios. Have cars, Helios, and Boa. Yes, Boa is a snake, and Helios the first person, and cars. I hope you know what cars are. English. So first we have a car. We have cars. It's, as you see, after R, even it's marked as end. Cars also follow CAR. So after the end of the word, you actually have another node called T, and which has a child called as. So your cars, bike will actually be another new root node itself. After bike, Helios, and then helicopter. Yes, against your array. So HELIO, which is common for Helios and helicopter, and after you add OS and you check for I, and the child of I is not actually C, so you create a new tree node, as evident over here. You created a new trie node, and you added OPTER, then board bow and that is a quick ladder. Yes, again, human H is common for human, helicopter, and Helios. So from H, it's checked for you, and you, since you are not a child, it added a new node and continues. And again, BOA, BOAT. Again, you understood white horse, BOA, BOAT, and BAT all start with B, but have different children. And now let us run it again. Okay, looks like I made some modifications by yes. Again, so now let's go through the actual sentence over here. So first you have I, and I is actually not the root of the tree node, as you see. The children of the root does not contain I, so it will continue to W, A, S, and all three are again not the children. R, I, D, I, N, G, again no children. A, and as soon as you reach C, you see that yes, from here you take C as center at the position J, and C is actually the node, and so you will go to the child of the letter. That means you will go to the C, and you will check for if it is the end of the word. So it's not. So now you will go for where is the sentence? And you check for A, and after C you actually have A, so you will tell yeah continue, and you will reach R, and R is actually the end of the word. So as soon as you reach end of the word, you will add it to the index and you will break out. I hope you understood why it works, how it works. Just do car story. See now why is okay. Now just think about it. Why is cars not coming? That is because it should not actually break out of this loop over here. Because after reaching R, and R is actually the end of the word, it should not break out. Because you have to search if the next letter, which is T, also exists. So now for an just a minute. Yes, I don't know. Yes, now you see that cards is also actually present. So first you check for you will see for C, and then you will see for R, and then you will see for T. And as soon as you reach CAR, you will see that R is actually under the word, so it break out. But then you check for T. T is actually present, so you will continue for S. And as soon as you reach S, you will get to know that okay, that is another end of the word. So you will add that also to the index. So the I will remain constant, but J is actually changing for each iteration. So after adding yes, and then you see that it's actually space, and space is actually not present in that triangle. So directly break out, and then you go for again A and D is not relevant. A is also not relevant, but you go for helicopter again. So far to reach H, E, L, I, C, O, P, T, E, R, and since R is the end of the word, we break, and then yeah, crash is not relevant. Yeah, crash is also relevant. So you first check for C, but and then as soon as you go for R, you will get to know that R is actually not present in the children itself. So we'll break out. Yeah, infrared is not relevant of me, and I got, yeah, scared is not also not relevant. And then we go for human, and you see that yes, H is present, U is present, M is present, A is present, and N is present, and N is actually the end of the word. So we'll add that index inside helicopter, and it again continues like that. So whatever you do, even if you change the ordering over here, even if you change the ordering over here, the ordering of how you get the data won't change, mainly because you're not actually iterating through the word, but you're actually iterating through the sentence. And yes, that's how correct algorithm works, and I hope you understood. And if you don't understand, then do obviously check out the video again, or there are many online resources. I'm not your dad, I'm not going to force you to rewatch my video or anything. And yes, that's how it works. Yeah, thank you for staying. If you stayed till now, goodbye.